for having inviting me here. I share my screen. Let me know if you can see it.
Yep.
Do you see the screen?
Yes.
Okay, now I turn in presentation mode. Okay. Visible?
Yes.
Okay, cool. So yes, the target of today is to talk about a framework that we developed to support decision making in production planning in the context of a European project that you cited before during my presentation. Okay, who am I? I think that Fabiano already spoke well, and I want just to present my small team in Sapienza. I'm part of a big team of process and service software engineering, and we have two major groups. So my group consists of these 5 people that are PhD student, research assistant, and so on. And we work on topics related to robotic process automation and process mining, on conversational system, on automated planning in artificial intelligence. And one of the topics that we focused in the past year was on improving the practice of automated simulation for production processes using process mining based techniques. And this is the focus of this seminar. In particular, I want to tell that this seminar is, so this result that I present today are grounded in a project that is called DataCloud. DataCloud is a Horizon 2020 project that lasted 3 years and finished on the end of 2023. We had our final review meeting on July of 2024, so a few months ago. Luckily, everything went good. The target of this project was to develop a software ecosystem for managing the big data pipeline lifecycle encompassing the computing continuum. What does it mean, big data pipeline? Big data pipeline are steps, are processing steps that are targeted to ingest data from different sources and move this data to a certain destination to perform further processing and analysis. So it's for this in particular, since this activity is quite computing intensive, in this project there was an intense use of the computing continuum. Computing continuum is a notion that integrate cloud computing with other technologies like edge computing, fog computing, with the target of, let's say, ensure low latency processing and to, let's say, to increase the parallelism of the computation. And we will see that for the framework that I showed today, the computing continuum as a role, let's say, to have good performance of the result that we have obtained. So in the context of this project, so in this project, the target of any partner was to define a specific small component of the process to discover the pipeline from data. This is the part that I was in charge of and Sapienza was in charge of. So discover data pipelines from data, and we use process mining for doing that. Define this data pipeline using a model, simulate this pipeline to choose the best cloud computing server to run them, search on the market the best, let's say, solution to deploy this server for cloud computing, and then adapt the scheduling of the server to optimize the computation. Okay, so this was a really software-based project. In the range of this project, there were some business cases that wanted to use this solution to solve some of their specific industrial problem. In particular, this project was validated against 5, I would say, heterogeneous business cases. because they involved the live streaming of football matches or higher mobile business revenues in smart marketing campaign. He helped patient data management, but in particular, I would say more I worked more with a business case related to the targeted to reduce the time to production and perform a better analytics in Industry 4.0 manufacturing. Okay, and now let's say this is exactly the business case we focus in this seminar. That is also, I think, the closest one to the topic of the Auto-Twin project. So about the impact of the project, were to lower the technological entry barriers to incorporate the big data pipeline into organization workflow. So if you are interested in this project, there are also many deliverables that are available. We were very lucky because this was the very first European project where we did not have any deliverable rejected, all were accepted anytime. So let's say it was a unique case. And if you're interested, you can find all the tool developed on this GitHub page. If you search on Google GitHub Data Cloud, you can find all the tool of the project. And if you want to see the vision and the impact of the project, there is this paper that we published in 2022 on IEEE Computer Magazine. So, but apart data cloud, I want to focus now on a specific business case of this project. And the business case of this project was related to was associated to a company that is called Catalano. So Catalano is one of the Italian leading sanitary-ware industries. So Catalano is an industry that targets to innovate the ceramic production, and it performed this by adopting many technologies that come from the Industry 4.0, so integrating robotic arms with a complex IoT infrastructure. So you can see on the right a promotional video Catalano, but the real industry is like that. So it's a almost fully automated industry. On the left, you can find the abstract production process of the company. The idea is that there is a first, after, let's say, having produced a 3D virtual prototype of a sanitary product, there is a casting phase that generates an initial mold model. Then this mold model is manipulated by the other step of the production process, concerned drying, glazing, finishing, firing, and quality control. There are some of these steps are semi or completely automated, other steps require the intervention of a human expert. So this production of ceramic items is a bit particular because during the production there are there can be many rupture, many deviation due to the problems of ceramic deformation. Ceramic deformation is let's say a well-known research challenge in that community, in the community of manufacturing of ceramic products, and let's say so. The adoption of a cyber physical system to monitor all the production process help to, let's say, decrease this deformation and decrease these issues. So this is the context of our framework, and this is one of the business case of the project. Let's see now the problem statement and why this business case was included in the Data Cloud project. So Catalano, like happen for many companies, experience a continuous stream of purchase order requests. Okay, so their production plant is active 24 hours per day, is every active. There is a long queue of product to be produced. The final user are customers, are normal customer, but the client are other companies that buy, let's say, batches, so many products at a time. And Catalano experienced a continuous stream of purchase order requests, and this order request must be manufactured and delivered by a specific time frame. So when there is a company that asks for example, 1,000 of sanitary products, these companies that are the end user for Catalano want also to know a quite precise date of delivery. And let's say answer to this question is quite complex for a company like this, because even if Catalano, like many other companies, is equipped with many production lines that work independently from each other, so having many production lines means that the production of different products can be parallelized until a certain extent, of course. The reality is that only a limited number of production orders can be, let's say, can be completed each day. And when there is a request of a new order, and the new order consists of a number of products and a number of different product type, well, to understand what is an expected delivery time, a suitable delivery time, there is a need of the intervention of expert user, because they have to consider many aspects to obtain this information. This aspect concern, for example, the production queue, because again, there is the plant is always active, and it is a long production queue of products that are already in queue to be produced. But the history of previously approved order, because there are orders that have, let's say, a major priority, that have more priority with respect to the other, but also the stock availability. You have to consider that these kind of companies have a huge warehouse of products that are in stock to try to satisfy all the customer demand. So all this information should be taken into consideration to provide, let's say, a quite almost clear answer to the end user about the delivery time of the product. I'll show you an example. So suppose that now the company is managing an order that include three type of item of kind X, item of kind Y, and item of kind Z. 50X, 500 items of kind Y, and 250 items of kind Z, with the, let's say, price of any item. And this is the state of the production. So this is what is happening now in the production plant. And in the warehouse, we have, let's say, 15 products of type X, 10 of type Y, and 5 of type Z. And the warehouse is still free. Free means that there is space for, let's say, collecting other items. Okay, now suppose that at a certain, this is simplified, of course, it's a simplified example. Suppose that at a certain point the company receive a substantial order for items of type A. And this type of type A are items that have a good priority for the company because their price is quite high. And let's say the order consists of 100 items of type A. So at this point, the company, in particular the expert user, by analyzing the production, can decide to, let's say, allocate the specific robotic arms that were, let's say, allocated for item of type X to the item of type A. So they can perform a substitution. Okay, and this, of course, this decision can, let's say, can be done for the pieces that are not yet produced, so that are in the queue. And of course, this decision includes a fixed waiting time because, let's say, in a ceramic company, let's say before producing a certain item, there is the need to switch the mold stamp. Particularly in this casting step, that is the first step of the production, there are these mold stamp where let's say, the mold of the product were put. Okay, so it is they need to change the stamp in order to start producing items of kind A. Okay, but it's not enough because the expert the human expert need also to adjust all the production parameter to set up the robotic arms to work with the items of type A, because according to the specific time of product, the robotic arms have different behavior. So there are many configuration aspects that must be done at a software for a software perspective, and other that require a manual activity, this switching of mold stamps. Okay, now suppose that we have done this substitution, and this substitution can be, let's say, done, and these decisions now are taken by a human expert. And while at this point item A start to be produced, in parallel, in the parallel production line, we continue to produce items of type Y and items of type Z. Okay? Suppose that at a certain point we complete Y and Z, the last piece of I is finalized, but the warehouse reach its storage capacity. So this is a situation that happens many times in at least in this specific company, so that the warehouse is full. And to produce new item is required to free the warehouse from existing order. But what happened at this point? That we cannot immediately start producing again items of kind X. So while on the one hand we have finished the first order, on the other hand we are stuck for the second order because the warehouse is full. And this, of course, creates delays, and sometimes the consequence of this is that some production line must be stopped for, let's say, a certain period of time until the warehouse is again free. So what is the message behind this example? The message is that a decision to prioritize a specific order with respect to another one, for example, must be taken after considering many aspects that are related to the products that are being produced, aspects that are related to the queues of the product. And this is a simplified version of the queue because the queue is very long. Aspects that are related to the warehouse, to the size of the warehouse, to the capacity of the warehouse. Okay, and all this information are dynamic, so they change continuously. So it is very complex for whatever human expert to, let's say, come with a good solution in a short period of time. Indeed, in Catalano, at least, now there are a couple of good human experts, a couple of skilled experts, probably more, but I remember a couple that analyze many Excel sheets with the production status, with the warehouse status, and so on, and then they take some days, 1-2 days, to take a final decision. Okay, that can be, let's say, I would say, suboptimal decision. Okay, so starting from this problem statement, now the question is, there are many conventional production planning tools that can help, at least, I'm not saying maybe tackle this issue is too strong, but help to support the human expert to address this issue. For example, Arena, Simio, there are many planning tools, and I guess that you know all these planning tools. Okay, production planning. Of course, again, this is something that it is very well known in the Auto-Twin project, I guess, but just for the people that do not know well this concept, production planning is focused on representing the operational step of the production process, together with the dependencies of the steps of the production process, the human and technological results, the overall schedule, and many other parameters that can be considered for plan the execution of the production process before executing it for real. The objective of a production planning tool, the main objective, are to, let's say, develop a kind of digital twin, so to mirror the production process life cycle by a digital model, and design an efficient way to, let's say, understand how to deliver the company's product with a good level of quality by meeting the customer demand. And in general, the customer demand is an on-time delivery. At least I'm talking now for the specific case study that I'm discussing, but for many companies, on-time delivery is one customer demand, but also trying to meet the organizational need. For example, try to reduce the cycle time, so the time from the start to the end of an instance of the production process. And there are many state-of-the-art tools that can support this task: the manufacturing execution system, product lifecycle management system, and the descriptive event simulation tools. So what are the limitations of production planning in a, let's say, context that is, let's say, highly immersed in Industry 4.0? The fact is that when we use this tool, we need to pre-specify our digital model. So we have to pre-specify our digital model by inserting all the information related to the time and cost of the production process step, the branching probabilities, the distribution of items that come into the production. There are many parameters that must be set, let's say, at the same time. But the reality is that any product type can have its specific production parameter. Sometimes these production parameters are not always the same, but they change over time, and they change over time because, for example, a specific machinery change, or because there are problems with the human resources and so on. So to keep this digital model up to date to the dynamic context of the Industry 4.0 company is quite complex, in particular if this activity is done manually. And the consequence of this is to obtain digital models that are a bit outdated. Outdated because they refer to picture of the production process that is not really up to date with the real, let's say, with the aligned with the real time context. And now the concept of context. So what is the context? The context in our vision is a concept that consists of some production-related information, like the time and cost associated with its production phase, the availability of the human workforce, the warehouse capacity, the priority of planned orders, but also external factors that are not directly observable in the execution of the production process. So this external factor is very complex to capture them in a traditional production planning tool. They are related, for example, to the market demand. This is very abstract. The landscape, the supplier relationship, and so on. So if this is our concept of context, our, let's say, problem with, so the problem of this company was that the usage of traditional production planning tool to solve the problem of predicting a specific timeline for an order. So the problem was a limited context awareness, because the decisions were taken by human experts, but not on the real picture of the production of the plant. And this led to a kind of static decision making. So decision making that is, let's say, blind to its focus on information about the production that is outdated. On the other hand, one of the targets of this company during the project was to have a digital model that could automatically self-adaptive to the context, to the dynamic context, and in particular, digital model not manually defined by the expert human, but obtained by the collected production data. So by the data collected during the production of the single product. Okay? Now, from this problem, we can move to the research challenge that the company fixed for this project. So the framework that I'm going to show you is a framework that is a general purpose framework, but at the very beginning, it was told to solve the problem for this specific business case, because again, this is one of the result of the specific result of this DataCloud project. So two main challenge for the Catalano company. First one, automated generation of up-to-date digital model from raw production data. Second challenge, so starting from this digital model that we can, let's say, the idea is to have context-aware digital model, considering our previous definition of context. So try to extract insight-ready data from this digital model to improve the quality of decision making. So this is the general idea of the framework. So starting from the three main databases of this company, this company provides three databases: a database related to the order, a database related to the warehouse, and a database related to the production. I want to, let's say, emphasize the fact that these databases are were developed on different DBMS and are absolutely not integrated from each other. So a human expert has to process them, let's say, in a very wise way, because there are completely separated information with potentially duplicate information, and there is not a real integration of this data. Starting from this data, they wanted a framework that, given any order, is able to analyze this data and understand, let's say, the best solution to, let's say, put this order in the queue, the best solution to put this order in the queue, to don't delay too much the previous order, optimizing the new order according to its priority, and in particular providing a precise delivery date, let's say a quite precise delivery date to the client. Okay, so this is a black box, of course, and together with the company, we try to open this black box and try to develop the anatomy of this black box. In particular, we focus to develop this black box by relying on simulation tools, by simulation algorithms. So our idea was to obtain the data, interpret the data, embed this data with the information of the new order, then utilize simulation algorithm to simulate different scenarios starting from this data, different potential scenarios starting from this data that include the new order. And this scenario can include, for example, moving order in queue, let's say, later in the queue and moving the new order before, or just put the order at the end of the queue. So many different simulation scenarios, and process them and then visualize them to support the final decision of the expert user. Okay, so that was the main idea behind the general framework. If we open this framework, we can find our implementation, our attempt of implementation of this framework that now I try to, let's say, present to you. Okay, let's start from the data, from the raw data. So starting from the raw data, the first idea was to analyze all the database, to obtain a collection of historical production data, because the historical production data contain historical information about the production of specific order type, but also historical information related to the behavior of the warehouse, for example, and other properties. Then this information were passed to a component that we call event log extraction. This component, called event log extraction, is able to generate an event log starting from this information. Consider that this part, let's say, is one of the most complex part of the entire framework, and is the part that required a certain involvement of the human expert, at least in first stage. I don't have time now to explain all the detail of this part, but at the end of the seminar, I will provide you a paper if you want to investigate this. But the idea is that with this historical production data, we obtain the incoming production data, and so related to a specific order. For example, a specific order can include some product type to be produced, wash basin, water closet, and so on, the quantity of this product, and the specific deadline. So with these three input, integrated with historical production data, we obtain an event log that is focused on the specific production of, let's say, of previous production of product types, wash basin and water closet, that are exactly the products, let's say, required for the specific order. So at the end of this step, the idea is to have an event log with the historical behavior of the production plant, in particular considering the specific, the information specific to the production type included in the order. Okay? This event log was then used to, let's say, try to develop a simulation model. To be more precise, we use the event log we pass the event log in input to two different techniques. One technique is well known also in AutoTwin, because in AutoTwin there is also process mining, and is called process discovery. So trivially, given the event log, the idea was to extract a first skeleton of the control flow of the, let's say, flow of operational step related to the past execution of products similar to the product that we have in the order. On the other hand, we obtain a parameter estimation. What does it mean, parameter estimation? Means that with the process discovery, we may have the flow, the order of operational steps, the order of the operational step of the production process. With the parameter estimation, the idea was to estimate all the quantitative information related to any step. For example, the time for a specific step of the production process related to a particular product type. For example, the distribution of time, distribution of cost, and so on. Information about the specific human resources involved in any step, the calendar of the resources. So all the parameters that I call them parameters, maybe in let's say, I know very well Andrea Matta, so Andrea Matta probably called them in another way. I call them parameter. For me, parameter are all those variables that are needed to feed a simulation planning tool. Okay, so time, cost, and all this information. And we obtain all this information by using a customized version of an algorithm developed by Marlon Dumas. I think that you had another seminar where Marlon Dumas explained in part this algorithm. So an algorithm to obtain simulation model from event log. But while in the work of Marlon, let's say this learning was more oriented to the learning of business process simulation model, let's say we developed a customized version of this algorithm that was more oriented to the production process, because we were also able to extract other information, like information about the queues, the work list, and so on. So it is a bit more oriented to the production. So with these two information, the process model, so the control flow, and the parameter, the production parameter, we then can have our simulation model. But the reality is that the simulation model is still not yet precise. It's still not yet precise because in the company, there are some steps that are not really well observable in the log. But there are some steps, like the casting step and the finishing step, that require the human intervention. So for this step, it was required to tune this simulation model to accommodate the requirement of this step. So let's say to be more precise, so the casting and the finishing step that are the first and the last step for the ceramic production are usually constrained by technological and physical limits that we need to consider when we develop our simulation model. Okay. For example, here there is an example. The idea is that we're in the casting step. Suppose in the casting step, the plant is equipped with n robotic arms, with a number of n robotic arms that are configured with the specific mold stamp of the product that the company is producing in that period. Let's say if we want to switch here mold stamps, this requires not only the involvement of the humans to change the stamps, but let's say the consequence is even worse because we have to really interrupt a production line to change the stamps. Okay, indeed, the company try to mitigate, to limit the change of production of mold stamps. Indeed, when they produce sanitary items, they produce sanitary items in batches before changing the order. This to mitigate the change of the stamps, of course, and to save time. So this is an aspect that is very important, and that it is not it cannot be directly obtained by the log, and it needs to be, let's say, put directly in the simulation model. So in this specific case, for example, we need to, let's say, personalize the simulation model by thinking to two distinct process activities, one for casting the wash basin and the other for casting the water cloth. Wash basin and water cloth are the two product types that we have in the order. So the idea is that we have at least two branches, one related to the casting of one product and the other related to the casting of the other product. This to optimize the assignment of the stamps. Okay, this information is not available here, but it's something that we need to customize with the help of the human resources during this model tuning and context management. And a similar consideration can be done for the finishing step. The finishing step is the step where there is a kind of quality control by the expert. Also here, let's say there are some aspects that are not directly involved in the event log and must be directly put in the simulation model. So there is this step that we call model tuning and context management that enable to make our simulation model even more context aware. So we increase the context awareness of the model to the specific product type that we wanted to obtain. Of course, guys, behind this there is a word. So I don't have time to explain everything, but at the end I will show you a paper that you can look, and there is let's say a complete example about this let's say real world case that we found in this company. After that, what we do is to generate many simulation scenarios, where each simulation scenario is a potential scenario that include the new order and include also the previous order. But the new order is put before a previous order, after another previous order, or the production is stopped, or the new order is splitted. So the idea is that we developed in this model tuning and context management, we have a software that automatically generates from hundreds to thousands of simulation scenarios that are very close from each other. There are small changes. All simulation scenarios are, let's say, quite suitable, But of course, all of them produce, let's say, different quantitative results, potentially different quantitative results. Of course, we don't want that a human expert analyze thousands of simulation scenarios, but our target is to run this simulation scenario using business process simulation technique. So in the first stage, we relied on a well-known engine developed for the BIMP simulation business process engine. But after that, since BIMP is really oriented to business processes, we developed our own simulation tool that is open source. We developed it using SymPy that is able to take a single scenario and, let's say, produce a complete simulation of it. Okay, trying to also obtain quantitative information after the simulation. What is the problem of this? The problem of this is that it takes a lot of time. So one simulation scenario simulating one single process can take a few seconds. Simulating thousands of simulation scenarios take hours or sometimes also days. Okay, so it's here that the DataCloud project plays a role, because this framework was thought not to run independently on a single server or on a single PC, but was thought to run on the cloud computing. So this image just showed that by increasing the order, the memory usage, let's say, more or less remain the same, but the CPU usage increase. This is just, let's say, a motivation to use the cloud computing. So the idea was, let's use the framework developed for the DataCloud project to run this specific framework for the Catalano company. This enables us to parallelize many simulation steps. So, for example, if we have an order number two. Order number two is an order that includes 150 items of product type wash basin and 150 items of type water closed. For the order number two, I don't put here the number of simulation that we generated, but to have good result, we needed more simulation, and in particular, we need to run any simulation many times to reduce the statistical noise after a simulation. But at the end, let's say, if we run this simulation one after one, we were able to obtain result after 2 days and a half. That is not good, of course. It's not acceptable for the company's operational need, because it is more or less the same time that is needed for a human expert. On the other hand, by parallelizing this computation using the computing continuum and the cloud computing, for example, by using 8 servers in parallel, we were able to reduce this computation to 7.8 hours. So we completely, let's say, reduce the computational time. This kind of optimization is called horizontal scaling. Okay, of course, let's say the target of the project was to demonstrate that the wise use of cloud computing and computing continuum resources was good to optimize the result for several business cases. Of course, to use or not to use this kind of resources is also a matter of cost, because reducing computation time may not proportionally reduce cost. But on the other hand, now using server, in particular reserving server, is not really cost expensive for companies. So it can be good to, let's say, rely on this horizontal scaling to optimize the simulation of many scenarios in parallel. Then, with these simulation scenarios, we feed this simulation scenario to a what-if analysis tool. So since the simulation scenario were 1,000.
Andreas, you have 10 more minutes. Okay, just pay attention to the time. Thanks.
Yeah. Thank you. Yeah. I'm closing. Indeed, I'm trying to go fast. Unfortunately, guys, for talking about this, I probably needed 2 hours. So with all the simulated scenarios, were passed to a what-if analysis component. Of course, we didn't want to show thousands of different results to the user, not suitable, not possible. So this what-if analysis tool were able to select the top X scenarios. In this case, we are shown the top 10 scenarios according to some specific KPIs. For example, cost, time, and the number of mold changes, because the number of mold changes was one of the most important parameters for the company. So the nice thing here is that the visualization can be customized according to the specific KPIs to be optimized. And the idea is that starting from this, there can be a kind of support for the human expert to decide which scenario is the best one to apply to put the new order into the production. Okay, I want just to show you very quickly a demo of the tool. So this is a demo of the tool. So the tool enables to add a new order of several type. So we are inventing the customer now. We are putting a deadline. So this is another input important at the end of the order. So during the creation of the simulation, we also consider the end of the order. So if there are simulations that, let's say, break this deadline seriously, we discard the simulation, of course. Okay, the quantity of any product, and then we can run the simulation. The simulation is run by calling our framework. Our framework is embedded in a Docker that is also available on GitHub if you want to try it. Then the Docker is executed by exploiting the parallel computation of cloud computing. And then here we arrive to the final step. The final step is the what-if analysis. So the what-if analysis that enable to, let's say, have an overview of the best simulation according to the KPI we are interested in. Okay, and we can also focus on specific bars, so focus on specific analysis. Okay, focus on specific scenario. So this, of course, is thought to support the decision of the user. So it does not substitute the decision of the user, but it's a support for the decision of the user. Okay, and there are many visualizations that the human expert can investigate. Now I skipped the validation of the framework that you can find in the paper. In particular, this is the paper I was talking before. It's a paper published in this year conference, International Conference on Advanced Information System Engineering. If you want more information about that, please ask me. I'm open to give them. I just want to close by emphasizing the limitation of this approach. First of all, data quality. If the quality of the obtained data, if the quality of the event log that we are producing is not good, and the quality of the data in the data source is not good, our prediction will be suboptimal. And if the data quality is bad, the predictions are dirty, are not really good. So data quality is an important aspect to be considered here. The second one is the contextual information. So the model tuning step, in our opinion, is crucial to make the model really context aware. But it is one of the steps that require really the presence of the human, require really the support of the human in the loop. So for this step, it is required to develop an intelligent tool, for example, by the use of large language model or similar tool that help the human expert to augment the simulation model in, let's say, a wise way. And finally, complex production scenarios. So this framework at the very beginning was not able to struggle with complex scenarios. So, for example, if the production required the presence of work in process jobs, so jobs that were in the production, these jobs that were in the production, well, they are not in the event log because they are in the production at that time. Okay, so these aspects were not considered in the framework, while these aspects are very important to be considered and to be integrated to have a simulation model that is even more realistic. So what we are working on in this period is exactly on a process mining based technique that also exploit a large language model and reasoning based technique to obtain not just information, not just historical information to build a simulation model, but a set of information that are related to the current production when the new order arrives. Okay, when a new input arrives from the external world. I talked about the order, but can be whatever input because the framework is general purpose. Okay, and I close here, and sorry if I went long as usual.
It's okay. Let's just give a couple of minutes for 1-2 questions. I see here one from Lior, so maybe we'll start with that one. Lior, you want to ask Andrea?
Sure.
Oh, okay. Lior,
you see the question?
Not really. I don't see the question. Can you read it?
So the question I like posing usually in these kinds of settings are typically about foreseeing unforeseen situations, which is usually the worry of the operation managers. Are they actually able to cope with most situations of incoming orders, or is there a way for them to foresee whether there may be some currently unforeseen conditions that they may need to adapt their production line in one way or another to accommodate for these gaps?
Okay, Leo, if I understand correctly, you are asking if you can deal with the situations that are unplanned, right?
Situation that may have partially been previously observed, but will put a lot of embarrassment with the current setup that needs some adaptation.
Yeah, of course, you are right. So this is a limitation because if you rely totally on the historical information, you are less prepared to unforeseen situation. That's why that's why we included this, let's say, model tuning step. In the model tuning step, you can increase your simulation model, so your historical perspective with some new information. Now, how to realize this model tuning step in a smart way, it's a research challenge because so far we did this model tuning step in a manual way. Okay, but of course this is not good to do it in a manual way because again we are putting all the burden to the expert of doing that. So probably there is a good, in my opinion, is a good step where a conversation, a kind of conversational framework can help the expert user to improve this model with new information that are able to that you can integrate in your simulation model in order to prepare your simulation before, let's say, the things escalate, for example. Okay, so yes, your question is very right. It's very right. So it's very correct.
Thank you.
Dario, a quick question. I see that you raise your hand. You are muted.
Sorry. As you know, in H2020 we have similar cases, and I really found that the challenges that you found are very similar to the one, because I'm Dario Marrella from TTS, we're the company which we are realizing the simulation models. Okay, we use our own discrete event simulation model to create simulations. So one of the questions was also from me. I had two questions. One was about this improving the context awareness, but to make it shorter, how much do you think? Because I think also that very often there is manual phase in making these models valid in the end at this stage. I mean, at least also for us. So how much do you think that it saves for compared to creating a model from scratch? Because it's something that we are also facing into our project. So how much effort is this content awareness requires?
So if I can answer to the first, so of course it depends by the amount of product of the production line of the specific company. So in my opinion, there is a piece, a fragment of context awareness that is I would call historical context awareness about time for a specific step, number of resources involved, and so on, that I think that can be included at the very beginning from scratch. So the issue is, in particular for this company, the issue is that the single step, the performance of the single step change over time. Because maybe you change a robotic arm, or you include a new sensor, or you include a new information. So for that case, let's say including this information from scratch, at least for this specific case that I shown, was highly complex. On the one hand, because you need the human expert that configured the sensor, the specific machinery for doing that, or you could not really do that in a precise way. You can also predict, estimate in the production model. So of course it can be done. It can be done, of course. The effort for this specific business case, because we tried also a conventional effort for them. I had a couple of theses trying the contrary. So we tried to build a simulation model from scratch to see if it was worth to have this framework at the end. And we were able to have a good simulation model related to the historical information. Not taken by the lab, but taken by interviewing the domain expert. However, when we went to move to the information related to, let's say, extracted from the sensor or extracted from the machineries, then the results were quite far from the reality. Indeed, so this framework is a result of a project, so it is not still used by the company because we are still working on it. Indeed, the company now use an hybrid approach. On the one hand, is using a model developed from scratch. On the other hand, the context awareness is given by the human expert. So when a new order arrives, the human expert take the simulation model with Arena, Simio, this kind of tool, and then integrate this information by looking at, let's say, 3 or 4 big Excel file with all the information about the warehouse, the order, and so on, and then manually take a decision. Okay, so the context awareness now is in the Excel file, the new context. So is it complex to put from scratch in the model? I think it's so maybe it's not complex. I'm not sure how it is outdated, this context awareness. Of course, it depends by the typology of the company. So it's complex to me to give a precise answer to that. But I see a gap between what you can put in the simulation model from scratch and what you can include later by embedding the information dynamically. Okay, so I know that is not the total answer that you wanted, but it's just a
no, but I understand
very complex.
which is complex.
Daria, maybe you can take that offline. We just need to close. Thank you very much, Andrea, for this interesting talk. And if there are further questions, then you can reach out to Andrea, I'm sure, by email. Okay. Thank you very much.
So thank you for the invitation. Thank you for letting me show this work.
Very
Bye,
interesting.
and good luck
Bye-bye.
for the project.
Thank you.
Bye.
Bye.
Bye.